Okay, perfect.
Great.
I guess we are almost ready to start the next session. This session will be mostly concentrated on basically facility, large-scale facility, synchrotron-based large-scale facility at Krakow in Solaris. And we will discuss about, first of all, project for about Ukrainian Beamline project and also different beamlines and different opportunities for Ukrainian researchers to perform their investigation at this research center. So, and I would like to invite you, as already was mentioned, Luc Patthey, who initiated the creation of Ukrainian Beamline at Solaris Synchrotron, and with his talk about Light for Ukraine project. So you are welcome.
Hello, do you hear me?
Yes, yes, yes.
So I will try to share my screen first. Hopefully it works. Here you are.
Perfect. We see everything.
Okay, thank you. Hello, everybody. I'm very proud to be actually here, and I would like to thanks Danilo Babiš to invite me to give you a little bit of hint of what we would like to do in the frame of Light for Ukrainians initiative. And so my name is Luc Patthey. I'm working at the Polcher Institute since more than 25 years. So first I would like to uh, tell you a little bit is if I can move to the next slide. Doesn't work. I'm just a moment. Yes, okay. Maybe a few words about first the Polcher Institute. Before we go deep in the project, the Polcher Institute is actually located in Switzerland. If you see this nice view from a helicopter, you see the Swiss Alps on the background with the Eiger, Mönch and Jungfrau. And Polcher Institute is actually located in both sides of a river which collect all the water from the plateau of Switzerland. And as you can see, here we have Synchrotrons, which is this Swiss light source. And we have another photon source, which is in the other side, in the wood, this, which is a free electron laser, the Swiss free electron laser, Swissfel. And I think what is very interesting and maybe a strong link with your foreseen community, Ukraine synchrotron and neutron community, is you can see then on site we have also a synchrotrons, a neutrons source facility. And I think we as a scientist profit quite a bit from this synergy between the photon source and the neutron source. So I'm just can encourage to actually link those two societies. Okay, so the Polcher Institute is part of the so-called ETH domains, which is actually a federal government high schools, which combines also ETH Zurich and EPFL, which is at Lausanne and in Zurich in the French and in German part. So basically, this slide for Ukrainians has been, as already mentioned, this morning's has actually been initiated by LIPS plenary meetings, which has been held in October 2022, which actually delegate Solaris to coordinate the actions of with the academic Ukrainian academic and researcher to actually promote possible light source for Ukrainians. LIPS, for your informations, is actually an association's a Liga of Urban Accelerator-based photon source, where PSI is part of it. There is also Solaris, which is part of it, and all the synchrotrons and FEL radiations around Europe. And so the motivations is really to give access to this photon source to Ukraine's scientists. The histories, as I said, start in October 2022. And it has been actually a nice online workshops, which is actually Light for Ukrainians in February 2024, where we try to discuss already the concept of building the beamlines at SOLARIS. And based on that, I have been the chance and the opportunity to spend a few months at SOLARIS to actually explore the possibility or the options to develop this beamlines at SOLARIS for this purpose. And the message has been well taken. And we had early this year a second workshops organized by our colleagues at SOLARIS for this Light for Ukrainians. And now we have this first Ukrainian synchrotrons and neutron community meetings, where I'm very pleased to be present here. And our goal is actually to build these beamlines and to have the first photons on the samples starting from 2026. So SOLARIS is a synchrotron in Krakow, which is actually 1.5 GeV rings, which has actually several straight sections available. And we start to discuss the different opportunity with my different colleagues of SOLARIS, Anna and Jakob, and also with Alexander, and also with my colleagues from PSI, Leni Rivkins, and also with Danilo. And we would like to actually, the aim is to build new beamlines here, which is about transferring an insertion device from SLS. I will come back to this point later on. And to build a beamlines which is about 33 meters, which fit extremely well in the new hall of SOLARIS, which is now available at SOLARIS. And we would like to build beamlines based on ondulators and with monochromatic beams with focusing properties to send the photons to an experiment, and with the beam parameters going from 2 to 8 kiloelectron volt with a fairly high flux density, which is up to the 10 to the 12 photons per second per 0.1% bandwidth, with also microfocus capability. And so far, as I understood from my colleagues from SOLARIS, you see here the ring, and this is a new hall which is completely empty, and we would like to build these beamlines here as a beamlines for Light for Ukrainians. So this project, for my participations on this project, has started since actually I'm involved at SwissFel, at the Swiss Light Source, the SLS, which is a facility which is in operation from 2001. And we start to actually upgrade programs for this facility, and which means a lot of components will be not used anymore, but high value components can be refurbished and used to other facility. And this is what I try to start to this project, to actually transfer some equipment from the SLS, which are not anymore used through this upgrade, and to move those equipment to SOLARIS. The SLS will go through an upgrade, which is called the SLS2 at PSI. The Holy Grail is actually to increase the emittance of these machines, or to decrease the emittance of the machines by more a factor 35, and which allow us, if you see here, we need to rebuild completely the storage rings, including the insertion device and the beamlines. And this is needed to actually move from a fairly flat and elongated beams, which is the SLS, to a very small beam and round beam from SLS2 to really investigate nano focusing properties on the new beamlines. And what we want to do with SLS2 is really to increase the resolutions on the samples. So you need for that to start with a very small source. And 2 days, we are on the good way to actually reach resolutions of moving from 30 nanometers down to 3 nanometers on the sample. But this upgrade starts in October last year, where you see actually the old machines. 1 month later, the tunnel was empty, and few months later, we started already the constructions. And this is how the machines has been looking like a few months ago. So now the machine is complete, and we already almost closed the tunnels with the concrete, and we aim to get the first beams by end of the year, if not January, beginning of next year. But this said, we have actually a few components like this ondulator, the so-called U19, which is an in-vacuum ondulator, which will be not anymore used by the SLS, which has been here removed from the tunnels and put in storage place, which can be used actually at the Solaris. And this is a quite important piece of equipment. This is the ondulator which produces the synchrotron radiations for this source. And in the first meetings for the Light for Ukrainians, we have been working, the people from Solaris has been organizing these meetings where we try to actually identify what will be the scope of the research for these beamlines. And as you can see in these diagrams, a big part has been actually dedicated for nano and macro X-ray spectroscopy, typically X-ray absorption spectroscopy, and also in the tender X-ray regimes, which is exactly the energy regimes where this ondulator can serve the beamlines at Solaris. So we believe now we have a very good source which is technically feasible to implement these U19s, as you can see here, at Solaris, and it will serve actually a nano and micro XAS, nano and micro spectroscopy beamlines, and serve the Ukrainian scientists for the future in the fields of catalytic, biology, energy materials, and physics. And this is really a joint effort between Solaris, Kiev, and PSI in the frames of the LIPS, which has been triggering this initiative. So the work has been done last year. Then I've been done last year was actually to understood what are the parameters of this ondulator in the rings. So first you have to know if the piano fit the rooms, and indeed it's fit the rooms, as you can see in these CAD drawings, and what is the partitions you can play with it. But first, I would like to give you a very short tutorial in synchrotron radiation. Synchrotron radiations, as you may know, of course, it's not new. It started already in 2017, where actually our colleagues realized that from storage rings where you have electrons turning at speed of light can, by each bending magnet, create synchrotron radiations. And they found that we could use these synchrotron radiations produced by these bending magnets for the purpose of light source to be sent on the sample. This synchrotron radiation is actually very focused. It's directed in a narrow opening angles from the bending magnets. And this actually, the important things for synchrotrons is to define not only the flux, so the number of photons you have per second, but also the brightness, the number you have per second, but also for small angles and for small surface and for small bandwidth, basically to have a very bright source. And from the beginnings of the X-ray source, we start with the X-ray tubes, with rotating anodes. We went actually to the bending magnet in the 17, as I described briefly just before, and we moved to wigglers and ondulator. It's actually where we are 2 days with Solaris in between the new type of diffracted limited source with SLS2 will be, and we will be actually on the apex of this curve with this SOLARIS project, or with this Light for Ukrainians beamlines at SOLARIS. So we will have a very good light source. This part is actually a new type of photon source, which is the FEL, which is out of scope from for synchrotron radiation. This is another topics. But basically, you can see then actually the FEL the synchrotron radiations has overpassed the well-known Moore's law in terms of brightness, and this means light for Ukrainian is really foreseen to have a bright future. How synchrotrons from ondulator works, you have actually the electrons, instead to go in one pole, it go on many different magnet poles, which are north-south alternated, and by each pole it emits light, and this light is actually go to interference and fulfill actually these equations where the wavelengths of the ondulators fulfill these equations related to the periodicity of the ondulator and the strength of the magnetic fields and the energy of the rings. At the end of the day, you end up with a discrete spectra with harmonics, the odd harmonics, which are here of high intensity, which are usually in synchrotron used, and you have the odd harmonics, which is a lower intensity, which is sitting here. And we try to see now what actually has been the sequential radiation spectra getting out of these machines from at Solaris, which is located here in the second straight sections. And the spectrums corresponding to the odd harmonics is very well represented from 2 to 8 kilo electron volt. Everything which is above 10 to the 12 is very useful in the field of synchrotron facility. And you see then you could actually have access to a lot of KH, going from potassium to nickels and also to LH, from very key components for all X-ray absorption spectroscopy. So these beamlines will be extremely suited for X-ray absorptions spectroscopy and spectroscopy in general for the Ukrainian society. However, you have an issues, because if you look the spectra, which is corresponding to the odd harmonics, you will realize then at Solaris, we have some kind of gap corresponding to the distance between these blue curved, because this part will be not accessible in the first stage at Solaris. So we find a way to actually bypass these things to also use the even harmonics, which is actually here normally at lower intensity, but at high harmonics, you see then the intensity of these even harmonics are comparable to the odd harmonics, and actually thanks to the emittance of Solaris, we will get even a very good beam quality for these beam lines using the entire range of the photons going from 2 to 8 kilo electron volts. And as you can see, the source will be actually from all the way the energy, a very high quality, as you can see in this analysis. Important things after the ondulator, you need the beam lines. And one of the beam lines which will be renewed at SLS will be the micro XAS. And we will be able to recycle the monochromator of these beam lines, as well as the first mirror, and to build actually these beam lines at Solaris with the U19 and the first mirror and the double crystal monochromator, when we will need to actually work on future development for focusing mirrors for these beam lines. And at Solaris, these beam lines will actually cover a very interesting energy range. You see here, this is the portfolio of science we do at SLS, which is actually separated in two big regimes, the soft X-rays here and the hard X-rays. And you see then actually there is so to say a gap between the soft X-ray and the hard X-ray. And Solaris will actually fill this gap by covering the tender X-rays, and which will be relevant for the energy, materials, catalytic and environmental science, chemical imaging, material science, for nano and microspectroscopy, and maybe even nano molecular crystallography. Our schedules actually is actually a draft here, but we had done our study in last year and this year, and now we have to really implement the different components. And there is a very important milestone in this, or there's two milestones we would like to achieve. By end of 2026, we would like to have the first photon on the samples. But for doing that, we need actually to reach a very important milestones, and we did it. This is actually having the first scientist working on this project, and I would like to here welcome Danilo Babiš, who will be who will start this project, leading this project starting on November this year. And I'm very pleased that Danilo accept to take this challenge and join the teams to build this, helping us to build these beamlines. Welcome, Danilo, for in this project. Our budget is about total kind of budget typically is between 5 to 6 millions. PSI will contribute to 1 to 2 millions as in-kind, contributing to ondulator and beamline components, but we still need to make more investments, which has been actually ongoing. PSI managed to actually get, we managed with the help of my directors and also Lenny Rifkins to get a grant from the Swiss SERI. This is the Secretary of State for Research and Infrastructure, and the Swiss National Foundations. We managed to get a grant of 1.5 million of Swiss francs, and this will cover actually 3 years project scientist positions for Danilo Babiš, and 1 year of engineer and also hardware investment. And with that, I think I just flash what actually Danilo research interest is. For more, Danilo will actually present a talk, so it's a little bit of publicity to his talk. He will actually discuss about microscopic identifications of the electrical field drive isolator to metal transitions in MOT insulator, which is summarized in this slide. With that, I would like to conclude my presentation to say the Light for Ukrainian Beamlines project. This ondulator will fantastically fit the SOLARIS rings to deliver photons up to 8 kiloelectron to high flux and match the natural emittance of the rings to use actually even harmonics on this, which is mandatory for actually doing gapless energy range for micro XAS beamlines and also for microfocus. I believe with these beamlines at Solaris, we will promote really the Ukrainian photon science in key research fields using synchrotron light source for the Ukrainian synchrotron and neutron community. And I do believe also that this is actually the premise to actually step towards actually having future synchrotron light source if possible, in the ground of Ukrainian country in a later stage. And I would like, with that, thanks also all people involved here, typically my colleagues from Solaris, which go from Jakob, Marek, Anna, Adriana, and all the people from the Beamlines, and also very thankful for all the useful collaboration with Alex and Volodymyr, who has been actually part of the discussions. And from my side at PSI, my director, Christian Rueck, Lenny, my direct supervisor, Gabriel Epli, from who I get this direct support, Hans Braun, who is leading the SLS2 project, where we can get these different equipments, and my colleagues from the insertion device, and of course, all the Swiss government confederations for the financings of this project through this research, Secretary of State for Education and Research and Innovations, and the Swiss National Foundations. Thank you very much for your attention.
Thank you very much for amazing talk. Is there any questions from participants? Professor Kurdu, can you okay, now it's good.
Maybe I have a question. Hi, Luke. Just tutorial.
Hi.
Tutorial question. In Swiss light source, where is the main improvement of the beam squeezing is located?
I'm not sure if I understood correctly, but let me repeat your questions. You asked me where are the main improvements for SLS2?
Yeah, I mean, which device is responsible?
Okay, yeah. Basically, it's really the low emittance of the ring, the rings, all the magnets, all the electron beams quality is play a role for that. And we had to
focus on magnets.
Yeah, yes. All the electromagnetic properties of the storage rings.
What about undulator?
And to make use of this low emittance, we need to actually replace those undulator, basically because to get these better beams, we had to raise the energy of the storage rings from 2.4 to 2.7 GeV. And because of that, we have to replace all the insertion device to readjust the energy range dedicated to the beamline. So all the undulator, for example, the U19 will be replaced by a U17, shorter period, to increase to retune the photon energy range of the beamlines. And we will be able also to have smaller gap size from the undulator. So it's actually many steps of improvement. The big steps is the machines accelerator, due to the designs of the magnetic layout. And here it's very complex. I will not be able to tell you the details here. The 12 achromat has completely changed the designs, and the undulator source also changed in design. So it's at two levels of activities to reach to this improvement of brightness to the sample. But first, the low emittance is a key parameter for this machine.
Is there any other questions in the public? Okay.
Sorry, I have one, maybe short question. Hello, my name is Mikola. I am from European XAS. Thank you for the presentation. Do you have certain vision for supporting maybe time result studies at this instrument in future as well?
I have short answer probably for that question, as I would be responsible. So basically we were looking for, on options to have like nanosecond, picosecond time resolve studies at that instrument. And now we're considering this option and looking on parameters like beam flux at the sample, which is important. And basically there is two options to perform it. Either you chop the X-ray and select the single bench, or you do it electronically by gating diode or detector. And basically now we're considering both options, and I guess one of them would be definitely available for users.
That's very good, because you will then bridge the gap to free electron lasers in future.
Yes, exactly. It will be not femtomax, or it will be not something like femto beamline, but still it will be something comparable to super XAS and XLS or ID9. But we will have to consider still we have to check any performance. But it's kind of coming automatically, and we are considering that option.
Cool. Thanks for the answer.
Okay. Thank you, Danilo, to answer the question.